My name is Dr. Michael Hargather. I am an associate professor of mechanical engineering here at New Mexico Tech, and I teach classes in fluid dynamics, thermodynamics, and I do research on explosives. This is a Z-type Schlieren system where we use it to look at density differences in the air. And the system starts here with a light source. We use a simple LED, and that LED is located at the focal point of this mirror. So the light comes out from the LED to the mirror, reflects off the mirror now as collimated light, and comes all the way back through what we define as our test section, and then off of this other mirror that's here that directs the light back towards the camera. And so this whole system of the path that the light follows makes a Z. And that's why we call it a Z-type Schlieren system. Right in front of the camera, what we have is a razor blade. And so this razor blade is what actually gives us the Schlieren effect, because it causes light rays that are bent anywhere in this system to interact with this razor blade differently. What we have right now is we have a simple candle here. And if we look on the monitor, what we can see is we can see this light-dark variation of the grayscale intensity. The work that we do is really to understand the fluid dynamics of explosion processes. And that includes the shock propagation, that includes how shock waves move and interact with objects. And it's also about the fluid dynamics of those gas processes with how they expand. So this is a lot of work that's similar to aerospace and aerodynamics research. And a lot of these techniques are also what you would find in supersonic wind tunnel testing. So here we're using the Z-type Schlieren system because we have mirrors. And we also do this with lens type systems, which we think of as just a straight line system with lenses. The real difference is the size of the mirrors versus lenses that you can obtain. So we're using the mirrors here because they're a little bit larger than the lenses that we have available. So we use a Schlieren system to study shock waves from explosives. And so we can use a high-speed camera to record the explosion process and then visualize the shock wave using the Schlieren system. So I have Sivana Torres, my grad student here, who's going to help us record this with the high-speed camera. Are we ready?
Yes. So here we have a Schlieren image of a simple snap pop. So you can see it's coming down into frame, and it's gonna hit the surface. And once it hits, you notice that it bounces a little bit, and then it will ignite and explode. And once it goes, you can see the shock wave that starts propagating through the field of view, and then you get all this turbulence that occurs due to the gas cloud, and then you can see all the fragmentation from the casing that it was in.
So we filmed this at 25,000 frames per second, and that really allows us to capture that shockwave propagation. When we think about a shockwave, it's moving at faster than the speed of sound. So speed of sound in air is about 340 meters per second, or about 760 miles per hour. So we really need to have a high-speed camera to be able to capture that shock motion.
I'm Sivana Torres, and I am a PhD student in the mechanical engineering department, and Dr. Hargather is my advisor. I use Schlieren imaging for my PhD research, and much like we use Schlieren for gases, we can also use it for solids. So I do shockwave propagation through PMMA, or optically clear materials. So you can see through this, and much like when you're imaging shockwaves propagating through a gas, you can also see the shockwave propagating through the solid material. And so one of the goals is to look at how this PMMA fractures. I did my undergrad here at New Mexico Tech in petroleum engineering, and I had taken a class with Dr. Hargather. I took thermodynamics with him, and he gave us a brief introduction of everything that he does, and I found everything that he did very interesting. I really enjoy fluids, so that's when I decided that I wanted to do my graduate school with him. I chose to come to New Mexico Tech because of the small class sizes. You get a lot of individual attention, and there's so many hands-on opportunities that you can have. I came to a reach out, like a high school reach out day through the MESA program because I'm from New Mexico, and I saw some of the things that they do here at Tech, and I thought that it would be awesome to come and have some hands-on experience with some of the things that they do here.
I think one of the best things about New Mexico Tech is that our students get real hands-on experience. I have multiple undergraduates that work here in my lab. They get trained on high-speed cameras. They learn how to set up these Schlieren systems, and then they get to apply it to real-world funded research. And it's not just understanding what you learn in the books, but it's learning here in the lab. It's learning doing research. It's learning doing the laboratory classes that are part of the education. And it opens doors for jobs. It opened doors for graduate school and really careers afterward.